Hello everyone, and welcome to Thermodynamics for Mechanical Engineers. What I want to talk about today is how do we approach thermodynamic cycles. Thermal is one of these classes that you either love or you hate. And I think people that hate it, part of the reason is that they see that there's all these things that we have to memorize, right? That every problem feels different, right? But I think that the people who love it look at thermodynamics and see that there's a systematic way that you can solve every thermodynamic cycle in a mechanical engineering thermodynamics class. So today we're going to look at how do we solve problems in thermodynamics when we're talking about thermodynamic cycles. So I like to think about how do I approach a problem, when I first open up an exam and I feel like I don't know what to do, right? So I look at that problem and I say, ooh, I really don't know what to do. And then you can fall back into this process. And as engineers, we know that when you have a good process, you'll usually end up with a good answer. So first, we want to define a characterization parameter for our cycle. Now, if it's a heat engine, we'll probably talk about thermal efficiency, but we have different characterization parameters for things like refrigerators or heat pumps. We'll want to do conservation of mass on all the elements inside of our cycle. We'll want to then do conservation of energy, or the first law, on all the elements in our cycle. Then we'll want to do the second law if we need to. Usually we want to do a second law analysis if the problem asks us if a particular process is possible. Next, we want to fix all of our states. Now, this often takes a lot of time in thermodynamics, but it's a very kind of mechanical process, right? We're looking things up in a table, right? But it is tricky, so we need to know what the working fluid is. Then, when we have the information on our state table, we'll try to determine things like power and heat rate for each component. Then we want to determine our actual efficiency, or whatever characterization parameter we're using for this particular cycle. And we'll compare that to maybe a Carnot efficiency or an ideal efficiency. So this list of 8 is hard for me to remember. I don't like to memorize things, and this feels like a lot of things to remember. So instead, I broke this down into 3 different questions. So the first is, how do I characterize the system? So what's the purpose of the cycle that I'm running? The second is it an open system or a closed system? Because that'll help me determine which versions of the first and second law to use, and whether or not I even need to do conservation of mass. Finally, the third question, which is important for all of these cycles, is what's the fluid? Because how I'm going to find things like specific enthalpy will depend on what the fluid is. And every different working fluid has its own tricks for fixing our state table. So let's look at some typical cycles that you might encounter in your thermodynamics class. I think the questions that we want to ask when we're looking at a particular cycle are, what's the energy benefit and what's the energy cost? If I group cycles that I might see in thermodynamics by energy benefit, I might want to look at heat engines. So my heat engines are typically interested in producing work or power. And in the case of a jet engine, instead I want thrust, right? So, but these are things where I'm trying to get sort of mechanical work, right? And if I'm trying to do temperature control, right, I'm either looking for something where the benefit is that I'm trying to cool down a place that's already cold, or I'm trying to heat up a place that's already hot. If I think about the energy cost, basically when I'm trying to get work, the cost is that I have to generate heat, often by burning things. And if I'm trying to achieve some temperature control, like if I'm trying to run a refrigerator to keep my food cold, then I have to plug that refrigerator into the wall to get some power. Next, I look at my cycles and I say, are they open or are they closed? Right? This is important because in a closed system, I have one set of equations for the first and second law, and in an open system, I have a different set of equations. Closed systems that you might encounter in an introduction to thermodynamics class include the Otto cycle and the diesel cycle. So these are internal combustion engines. Remember, they're not really closed systems, but we model them that way. And then open systems are things like Rankine cycles, refrigeration cycles, heat pumps, Brayton cycles, jet propulsion, and Brayton refrigeration. So the next way that I can categorize these different cycles is by what the working fluid is. Now remember, knowing the working fluid is going to help me find what properties I need to find in order to fix my state table. So I need to know, is it something where I'm changing phase? Do I need to know about the vapor dome and what the phase of the fluid is? Or is the working fluid an ideal gas, right? And if it's an ideal gas, how do I use the ideal gas law and maybe some isentropic relationships to try to fix my states? So cycles where we have a liquid vapor fluid or a vapor dome include the Rankine cycle, refrigeration or heat pump. And if I'm talking about an ideal gas, we might look for Otto cycles, diesel cycles. So those are our internal combustion engines, a Brayton cycle, jet propulsion, or Brayton refrigeration. So when I have a vapor dome, this sort of what's the working fluid question is really always a two-part question. When I have a vapor dome, I need to know what's the phase of my working fluid. Is it a subcooled liquid, a two-phase mixture, or is it superheated? And if it's air, I need to know, how am I going to model the air? Am I going to model it as having a variable specific heat where I have to look numbers up on a table? Or am I going to model it as constant specific heat where I can use something like m dot times Cp delta T to find the change in specific enthalpy? Thank you, and I'll see you next time on Thermodynamics for Mechanical Engineers.